Now we have section 8.3, an introduction to functions. We're going to start off by talking about relations. A relation in math is a pairing of elements of one set with elements of another set. When we have a relation, we have our two sets. One of them is called the domain, which is the set of all input values. The other is the range, which is the set of all output values. To make a relation into a function, we have each input corresponding to exactly one output, meaning input values cannot be repeated or used more than once. However, output values may be repeated. So in our first example, we are to determine whether the relation is a function, and if so, state the domain and range. Our first example, our input are the students, our output are the ages. So I have student Bob, age 18 and 20, student John, age 18, Bill, 21, and Mark, 20. So just a reminder, these students are the input, the ages are the output, and this example is not a function because Bob has two outputs associated. So we set up here, input values cannot be repeated. Bob is repeated into two different ages. So let's rearrange our input and output a little bit. Now our students, we have Bob is 18, John is 18, Bill is 21, Mark is 20. This one is a function because each input corresponds to only one output. Since it's a function, we can identify the domain. The domain will be the students. And the range will be the ages. Next, let's look at our input and output as ordered pairs. When we have ordered pairs, the input are the x coordinates and the output are the y coordinates. So to determine if a set of ordered pairs is a function, I look at my input values, each of the x's. There is nothing that repeats, so yes, it is a function. Since it is a function, we can identify domain and range. The domain is the set of all the x values. The range is the set of all the y values. Looking at letter D, to tell if it's a function, I look at the x values and I notice a repetition. Therefore, this is not a function. When we are working with equations, we have a function. When we substitute values for x, there is only one answer for y. Common examples of things that are not functions would be a plus or minus sign in front of the x, y being squared, or the absolute value of y. So in our next example, we have some equations. And to determine if it's a function, really what we're looking for is one that's not a function. It's not a function with those three cases I listed. There are other ways to make things non-functions, but these three that I've listed are the ones that you'll see. So letter A does not have any of those cases. So yes, it is a function. In fact, all linear equations, this is linear because x is to the first power and y is to the first power. All linear equations are functions. Letter B is not a function, and letter C is also not a function. When we are working with graphs, we tell if something is a function by what's called the vertical line test. A graph represents a function if and only if every vertical line intersects the graph in at most one point. So I have some pictures of some graphs. And letter A is a function because I could sketch in vertical lines and every vertical line is only hitting the graph once. Whereas letter B is not a function. I have the y-axis as a vertical line, it's easy to use, and it's hitting the graph 2 times. Letter C is also not a function because I have a vertical line. In fact, I could draw any other vertical line either. I could draw a vertical line right here and show that it's not a function. I could draw it over here. If there's any spot, even if there's just one vertical line that hits twice, then your graph is not a function. When we do have a function, we use what's called function notation. It's f with parentheses around the x, and that is read f of x. It's used in place of a y in an equation. The value that's put in the parentheses indicates what to substitute in place of the x. For example, f of 4, you're going to sub x equal to 4. F of t, you're going to sub x equal to t. So in example 4, find the indicated value of each function. I'm going to substitute a -3 in place of the x's. Every single x in the problem changes to a -3. And this on the left, f of -3, is just notation. So you don't do anything else with f of -3. You leave that alone. You solve out the right-hand side using order of operations. We get 18 plus 3, which is 21. We can use different letters. It's not always F and X. Letter B has G of A, and then later on it says G of -2. So I'm going to replace all of the A's with -2's. And solving the right-hand side, that's 2 plus 5, which is 7, and the absolute value of 7 is 7. A little word problem. Number of cars represented by capital N produced at a factory in one day after T hours of operations. And we have our function. And we're told the time is between 0 and 10. That just means that the factory is only functioning for 10 hours out of the day. Right? Identify the dependent variable and the independent variable. So for the dependent variable, actually it's easier to identify the independent variable. The independent variable is the variable whose value we choose. So we can choose values for t. So time, or t, is our independent variable. And then the dependent variable is going to be, in this case, the number of cars. It's the variable that depends on what value we chose for t. And in this case, it's going to be the number of cars, which is the capital letter N. Then we are asked to evaluate N of 4, so that's easy. Just put in 4 for the t's and solve it out with correct order of operations. 5 times 16 is 80, so that's going to be 320. Provide a verbal explanation of the meaning of N of 4. So what that means, 4 is our time. So after 4 hours of operation at the factory, 320 cars were produced.